We were talking last time about, well, we asked questions like, how do we know there's an atmosphere? I wanted to follow that up a little bit more. Someone had mentioned atmospheric pressure as being something that's really important for knowing there's an atmosphere. And I said, well, we don't really sense it very well because our bodies tend to equilibrate inside and outside. When we go up in an elevator, we're moving into lower pressure, but we may feel it in the ears, but we don't feel it most other places on our bodies. But then I was thinking there are some other ways that we could sense pressure. And I had these suction cups in my office. They're not sticky in any way, but when you push them together and remove the air that's inside, then you only have the atmospheric pressure acting on the outside and nothing on the inside. So when you try to pull them apart, try that. Watch out for your elbows there. Everybody gets to try that today. So you'll see that's atmospheric pressure, right? Again, watch the elbows so you don't get the guy next to you. Now, you were walking up to class today, and you remember that we got a piece of advice that I gave you for this course is to develop a habit of looking up in the sky. And what did you see this morning when you walked to class? Blue sky. Now, what if there had been no atmosphere? What would you see when you looked up? Black. Right, so that blue sky is light that's been scattered to your eye by the molecules in the atmosphere. So that's a good way to know there's an atmosphere. Another one on the pressure. When you're having lunch, if you're drinking from a straw, I don't know if you do that, but when you're drinking from a straw, you may think you're sucking that fluid into your mouth. Actually, you're not. You're dropping the pressure a little bit, but it's the atmospheric pressure pushing down on the top of the fluid that's actually what's pushing it up the straw. So you're not doing much. The atmosphere is doing most of that with its atmospheric pressure. So we'll continue to think about these day-to-day ways in which we will know that there's an atmosphere. Are there any questions on these issues before we begin? Any things we spoke about last time? Nothing? Okay. Well then, I want to move on to a subject today which is related to what we had last time, and that is which planets have atmospheres and why? And it turns out that the key physics, the key process that determines this is whether molecules at the top of the atmosphere can escape the planet's gravitational field. Now, let me be clear on this. The molecules in this room are traveling a very short distance, and then they encounter another molecule and they collide, and then another short distance and they collide. So there's no chance that these molecules in the lower part of the atmosphere could ever escape, at least not immediately, because they're surrounded by other molecules. But the molecules at the top of the atmosphere, if they're heading upwards, and some of them are, they might just leave. They may just get fed up and decide to leave the Earth's atmosphere. So we have to come up with some way of understanding that process and to find out when it works and when it doesn't work. So to do that, we need to define something called the escape velocity. It's defined as the velocity needed to escape from the gravitational field of a planet. Now, if this was a course in physics, we would derive it. It's not a difficult derivation, as it turns out, but I'm just going to give you the formula for it. V escape is given by the square root of twice times little g times big R Little g is the surface gravity of the planet. For Earth, by the way, I think you know what that number is. G is 9.81 meters per second squared. It's given in units of acceleration. In fact, it's just the rate, if you drop something, it's the rate at which it accelerates towards the surface of the Earth. And big R in this formula is the radius of the planet. Now, to be consistent, oh, by the way, for Earth, this is about 6371. The Earth is not exactly spherical, so this number is a little different depending where you are. It's about 6,400 kilometers, the radius of the Earth. So let's work out an example of this and then see what it means. So for Earth, then, v escape, let's compute it for Earth. It's going to be the square root of 2 times 9.81 times the radius of the Earth. We have to work in consistent SI units, international system, or so-called metric units. So I need to convert that to meters. So that's going to be 6370, and then 3 more zeros to get it into meters. And you know how to do a square root on your calculator. That comes out to be 11,180 meters per second. That's the escape velocity for planet Earth. Now, it's going to be different for other planets because they're going to have different surface gravities and different radii. But that's the escape velocity for planet Earth. So what does that mean? If I'm at the top of the atmosphere, there's the Earth, there's the atmosphere, and if I've got a molecule at the top that happens to be heading upwards, if it has a velocity less than this number, it's going to go up for a while and then stop, and then gravity is going to bring it back to the back into the atmosphere. If I have a molecule that's moving faster than that speed, it's going to leave. It will never be seen again in the vicinity of planet Earth. So this here is when the upward velocity is greater than v escape, and this is when v is less than v escape. Something interesting about this formula, notice that the mass of the object that we're talking about does not enter into that formula. So this would apply for a molecule or for a rocket ship. When they launch a rocket into orbit or to another planet, it's exactly that same speed that they have to accelerate the rocket to in order to get it to escape from our planet's gravitational field. So this is kind of a universal number for the planet, independent of what the object is. Any questions on that? So that's pretty helpful, but it's only half the story because we have to know something about what the molecules will be doing. So the typical speed of a molecule I'm going to call it V sub MOL, is given by the square root of 3 R bar T over capital M. Now, this is a formula you might derive in a chemistry class, and maybe you've seen this one before as well. In this formula, R hat is the universal gas constant. T is the temperature. Of the gas. It must be expressed in kelvins to work in that formula. That is in absolute units. And what else do we have there? M. M is the molecular weight of the molecule in question. Now, I think you know how to go back and forth between temperature units, but let me just remind you, if you've got a temperature in degrees Celsius, you have to add to that approximately 273.1. Sorry, that's an add. Temperature in Celsius plus 273.1 will give you the temperature in kelvins. Kelvins is on the absolute scale. Before we go any further, let me just give you a little table of these molecular weights for a few of the gases that we might be interested in. I'll make a table here for a single hydrogen atom by itself. It has just one proton in its nucleus and no neutrons, so its molecular weight is 1. This will be the column of molecular weights going down here. Hydrogen usually occurs in the diatomic form, two atoms fastened together with a bond, and of course the molecular weight for that would be 2. Helium has 2 protons and 2 neutrons in its nucleus, so it has a molecular weight of 4. Nitrogen, and most of the gas in this room is nitrogen. It appears in the diatomic form, two nitrogen atoms together. Each one has a mass of 14, so the molecular weight of the N2 molecule is 28. Oxygen, which composes most of the rest of the gas in this room, again occurs in the diatomic form. Each one is 16, and so that's going to be 32. And carbon dioxide, which you're breathing out, carbon is 12. If I add that to 2 O's, I'm going to get 44 for the molecular weight of carbon dioxide. So you've probably seen those numbers before, but that's what I'm talking about when I refer to the molecular weight here. Any questions there?
What is the R expressed as? Like, because there are like different numerical values. Like
the units of it? The question is about the units on universal gas constant, and I usually give them this way. I usually write them as units on that would be joules per kilomole per degree Kelvin. By the way, either at the end of this period or the beginning of next, I'm going to spend about 15 minutes talking about units. And so if you're a little bit rusty on units, stand by. We're just about to give a review of the units, especially in the SI system, which we'll be using in this course. Thanks for that question. So let's do an example then. Let's say that the temperature, here's my example. Let's say I've got a gas that's at a temperature of 15 degrees Celsius. Well, that's going to be about 288 Kelvin. If it has a molecular weight of 2, that would be hydrogen gas. We can put those numbers into the formula. It's going to be 3 times, I didn't give you the value, did I? The value for R hat's about 8314. Plus some other decimal places after that. But so let me work it out in this case. So it's going to be V molecular square root of 3 times 8314. Temperature is going to be 288. We're going to divide by 2. And for that, I get 1,894 meters per second. And let's do it immediately for nitrogen, because that's the one that's relevant to this room. So for a molecular weight of 28, well, the formula is going to be almost the same thing, isn't it? It's going to be 3 times 8314 times 288, but in this case divided by 28 inside the square root, and that comes out to be 506 meters per second. So that's what typically the molecules in this room are doing. That's That's pretty fast. I mean, that's something like 1,000 miles an hour. Those little molecules are really moving fast in a temperature, in a gas of the temperature that we have in this room. So now we've got the two sides of this argument started. It's time to do some interpretation of it. I wanted to consider for a moment what would happen if V escape was approximately equal to V molecular. In other words, if those two numbers were about the same value in an atmosphere, what would happen? Well, at the top of the atmosphere, some of the molecules are moving down and some of them are moving up. Now, I have to say, this is a typical molecular speed, but some of them are moving slower and some of them are moving faster. There's a complete distribution of speeds. So it's not every molecule that would be aiming up and have a speed equal to or greater than the escape velocity. Probably only a quarter or a fifth of the molecules up there would happen to be aiming up with a speed that would be fast enough to leave. But remember, they would leave in an instant. In a fraction of a second, they would be gone. In another fraction of a second, the molecules remaining would have had more collisions, and now some of them would be aiming up with a speed faster than the escape velocity, and they would leave. And this would continue. So in fact, if this were the case, if the average molecular speed was about the same as the escape velocity, we would have an explosive loss of the atmosphere. It would be gone within moments. So when we're asking about whether a planet can retain an atmosphere, we have to use a more restrictive criteria than this, because remember, the Earth has been around for something like 6 billion years. So we have to use a conservative estimate. The one that I like to use is to say the escape velocity, if that is greater than about 10 times the molecular speed, then an atmosphere can be retained. It's kind of a rule of thumb to put that factor of 10 in there, to take into account the fact that some molecules are moving faster than the typical molecular speed, and we have to retain it not just for an instant, we have to retain it over millions and millions of years. So let's take a look at Earth for a second and see what we can conclude from that. If I multiply this by 10, I get 18940 meters per second, about 19,000 meters per second. That is actually greater than this. And so we conclude from that that hydrogen could not be retained on Earth, could not be retained on Earth. You follow that logic? Any questions on that? Let's do the same thing for nitrogen. If I multiply this number by 10, 5060, that's about 5,000 meters per second. That's only half of this number. So we conclude that nitrogen could be retained. Well, as it turns out, there's very little hydrogen in our atmosphere. And that's probably why, because any hydrogen that was there in the beginning has been lost by this process. Instead, our atmosphere is dominated by nitrogen, mostly, but also oxygen that would move even a little bit slower because it has a molecular weight even greater. So that could be retained. There's some carbon dioxide in our atmosphere. That could be retained. So we've already learned something about the Earth with this little exercise. It's probably lost its light gases like hydrogen and helium, even if it was there in the beginning, which I think it probably was. But it's been able to retain the somewhat heavier gases, such as nitrogen, oxygen, and carbon dioxide. Questions on that? Yes?
Is there a way to determine how fast and when the Earth will release a certain gas?
Well, you'd have to go beyond. This is kind of a crude argument. It doesn't tell you the rate. You'd have to know, to do that, you'd have to know something about the rate at which molecules are colliding and restoring that set of molecules that are aiming upwards. It would depend on that to a certain extent. And there are some other processes that may play a role. For example, the solar wind coming from the sun will sometimes take the light molecules and sweep them away. I've not included that in this argument. So there's a few other things you'd have to include to get a quantitative estimate of that. This I have to admit then, that's a good question, and this I would say is more of a qualitative or an approximate approach to that question. It doesn't include all the physics, and it doesn't give us a quantitative answer of how rapidly the atmosphere would be lost. So, but that's what we can do with what we have here. Other questions? Yes?
Where does the 10 come from?
Well, it's a fudge factor. I admit this. The question is, this factor of 10, where did it come from? What I've done is try to use a number that is consistent with some of these more sophisticated calculations. You can find in the literature people have worked out this problem in great detail because it's of central importance to the history of the Earth. And from those complicated calculations, I've extracted this as kind of a rule of thumb. So I don't know that I would rely on this, but it gives us a rough estimate of how to judge things. I'm going to show you in a minute that this argument makes some sense when you look at all the planets together as well. And that won't necessarily confirm that that factor 10 is right, but at least it'll give us a sense that the argument is approximately correct. Okay, now, so what I did following this kind of a argument was to take all the planets and moons in the solar system, and I did an estimate for the temperature of each one, and we know something about the gravitational field and the radius of each planet, and so I came up with a ranked list where it's basically the ratio of the escape velocity to the molecular velocity. Sorry. If a planet has a large escape velocity and a small expected molecular speed, I ranked it high on the list. If it has a low escape velocity, like a small planet, not much gravity, fast-moving molecules, I put it low on this. So this is a ranked list, my ranked list of where I would expect to find atmospheres in the solar system. What's going to be first on the list? Jupiter is going to be first. Why? Yeah, so Jupiter has the largest mass. It's also fairly far out in the solar system, so the gases are not particularly hot. So this is large, and that's pretty small. So indeed, Jupiter is first on the list, and right behind it comes Saturn for similar reasons. Neptune, Uranus. Then comes our planet, Earth, Venus, Pluto, poor Pluto, no longer a planet, Triton, which is a satellite of Neptune, or say a moon of Neptune. Then comes Mars. Then comes Titan, Titan, which is a satellite of Saturn. And let me continue the list a little bit longer. Ganymede, Io, Callisto, Europa, Mercury, and our moon, and then I stopped there. Of course, I could go on and on because there's lots of other smaller moons in our solar system, but I wanted to get at least to Mercury, which is the other planet, and I wanted to get to our own moon in order to make the list interesting for us. So that's the rank list. Now, we know a lot about this because we can detect planetary atmospheres from a distance. We can detect it by going there with an unmanned vehicle. So we know pretty much whether these objects have atmospheres now. And I can draw a line under there. And actually, the line is right where I broke the columns. That's roughly the line. From observations, we think that these planets have atmospheres, and these do not. So our ranking based on that was pretty successful. Maybe not quantitatively, but at least qualitatively, it gave us an idea of where we could find atmospheres in the solar system. Other questions on that? It's a pretty simple argument, and I think pretty powerful to give us that kind of good result. So let me try to make a little sketch of the solar system then, because there's a little more that has to be said about this. Because remember, what I didn't bring into here was the molecular weight of the gases. I use a constant value for capital M as I did these calculations. So if we've got the sun here, then going out in order, you've got Mercury, Venus, Earth, Mars, and then quite a bit larger. I'll draw these with a little bit of size to them. But then quite a bit larger, you have Jupiter, Saturn, a little smaller, Uranus, and Neptune. So now let's consider this molecular weight effect, the heavy gases versus the lighter gases. For Mercury, it turns out that both would be lost. I'm going to put two arrows here, and I'm going to label one L and one H. L for the light gases, like hydrogen, and H for the heavy gases, like nitrogen, for example. Mercury would lose them both because it's a pretty small planet, and it's quite hot. So if there were molecules there, they'd be moving quite fast. Venus, the light gases can leave, the heavy gases are retained. So I've drawn that molecule trajectory coming back into the planet. The same for Earth. The light gases leave, the heavy gases come back. The same for Mars. But for the outer planets, both the heavy and the light gases come back. I'm tempted to put a little face on that. No, so that gives us some idea of what particular molecules can be found on individual planets. We're going to find only heavier gases in these three planets, Venus, Earth, and Mars, but we can find heavy gases, but also the light gases. The hydrogen and the helium can be retained for those outer, more massive planets. So while we have this up here, let me talk about a couple other characteristics of planets that have some interest in relation to atmospheres. For example, here's a category of whether there is a solid surface. Solid surface. Something you can stand on. And the answer is yes, 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 no, 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 no. What happens if you sent a spaceship to Jupiter and tried to land on the surface, you would penetrate down into this massive atmosphere, and it would get denser and denser and denser. And after a while, you'd begin to wonder whether you're in a gas or a liquid, but there wouldn't be any particular interface. Eventually, as you came further down, you're pretty sure you're no longer in a gas. You're almost certainly in a liquid. And as you kept going down, it's going to get a bit more and more like a solid, perhaps, but never with an interface, all right? So the point is that there's no surface. There's no solid surface on these outer planets, whereas the inner ones you can. You can land on it, walk around. They may be hostile in terms of their environment, but at least there is a place to stand. What about the temperature? Well, you know, extremely hot and no atmosphere on Mars. This one's Venus is extremely hot as well. Earth, well, we live there, so it's okay, I guess. Mars may be okay, but it's a little cold for us. It's below the freezing point of water most of the time. And for these others, well, you know, I don't know what to write down because here I'm kind of assuming that I can stand on the surface and break out a thermometer and measure the temperature. But if there's no solid surface, then what temperature do I use? So I can't really fill this in because it would get hotter and hotter and hotter as you go down deeper and deeper in the planet. There isn't any particular reference point from which to say Jupiter is a hot planet or Jupiter is a cold planet. The question is really, I would say, ill-posed because there's no solid surface. What about habitability? I think you can pretty much guess for yourself then that these wouldn't be habitable for a number of reasons, and neither would Mercury and Venus. Our planet Earth probably, certainly yes, and Mars would be, well, it'd be a question mark. I mean, there's not very much atmosphere there. You might be able to build some kind of enclosure and live inside some kind of a pressurized enclosure, but it wouldn't be a very pleasant existence for us. So habitability is pretty much limited to Earth and maybe Mars if you want to extend the definition a little bit. Questions on that? Give me just a minute. I want to show you a few things here. So this is the diagram I already really have on the blackboard. It's not to scale either. I mean, these distances are not to scale, but you get some idea of the fact that these inner planets are a lot smaller than the outer planets. For example, we know Jupiter has an atmosphere because we can see these cloud patterns moving around at very great speeds. And the great red spot, which I don't think is shown there, is a giant vortex like a hurricane, but 1,000 times the size, sitting in Jupiter's atmosphere, winds swirling around it. So it's obvious that Jupiter has an atmosphere. But so do all of these, and so does Mars and Venus and Earth. It's only Mercury on this diagram that does not have a planetary atmosphere. So it's convenient to break up the planets into two general categories, the so-called terrestrial planets, which are a bit like Earth. They comprise Mercury, Venus, Earth, and Mars. They're small, they're dense, they have rocky surfaces, they rotate relatively slowly on their axis. For Earth, it takes, as you know, 24 hours to go around. The atmosphere, well, none in the case of Mercury, but the heavier gases in the case of Earth, Mars, and Venus, with molecular weights somewhere in the range of 4 to 50, I would say. Whereas the Jovian planets, that is the planets that are like Jupiter in some way, are much larger, much lower density. They have soft surfaces. They rotate more rapidly than Earth, and their atmosphere is primarily composed of light gases, mostly hydrogen with a molecular weight of 2 in the diatomic form, and helium, just independent helium atoms with a molecular weight of 4. So there are the terrestrial planets. I'll show you more about this, but that's Earth, Venus, Mars, and Mercury. And the outer planets, the Jovian planets. That's the list. I already have it on the board, so you don't have to write that down again. But then this is also review. I think we've been through this. But Mercury has no atmosphere. Venus has a massive CO2 atmosphere. It is entirely covered by clouds, 100% cloud cover all the time, which makes it a very bright planet. In fact, do you know the colloquial term for Venus among astronomers or farmers or sailors?
Is it called like the greenhouse planet or something?
No, not colloquially. The evening star. It's called the evening star. That's an odd name, isn't it? Because it's not a star at all. But when the sun sets in the evening and the sky darkens, that's usually the first thing you can see. So the evening star, they call it. Why is it? Because it's, well, it's relatively large, relatively close, but it's very bright. It reflects, it's completely covered with white clouds, reflects a lot of sunlight, and makes it easy for us to see. It turns out, though, that it also has a super greenhouse effect. And it's a little bit closer to the sun than we are, but its temperature is even hotter than you would expect based on that proximity to the sun. It has a really super greenhouse effect that brings it up to a temperature that's in the order of 600 Celsius, way, way, way above the boiling point and so on and so forth. So a very hot planet because of the greenhouse effect. The Earth we know has nitrogen, oxygen atmosphere primarily, partly cloudy. Water can exist in the liquid form. We have life, and we have ice caps. We have frozen water in this case in the form of snow or frozen seawater at the caps, at the poles of the planet. Mars has a CO2 atmosphere, but not much of it. There may have been water there once. We don't know if it's still there now. There may have been life there once. We don't think it's there now, but it too has some ice caps. If you look at the planet, it has these kind of snowy regions near the poles. We don't think it's frozen water. We think it's frozen CO2. What's frozen CO2 called? Dry ice. Yeah, dry ice is what we call frozen CO2. Mars seems to have dry ice caps on the poles that change a bit with the season. Now, so the point here, we're not going to be studying in the rest of the course much more about these other planets, but the point of today's lecture is to put Earth in some kind of context, especially in relation to how our atmosphere is composed, how it's retained. Later on, we'll be talking about the greenhouse effect on Venus and why that might be a concern for us. Questions here? So there's Mercury, a rugged surface, pockmarked with meteorite collision craters. Remember, no atmosphere. There's Venus. Now, neither of these pictures of Venus is taken in visible light. What you would see with your eye is a uniform, featureless white surface. When you look at it in the ultraviolet, you begin to see a little bit of difference between some of the clouds. And these would be moving very rapidly around the planet if you had a movie of this. So you can distinguish a little bit low clouds from high clouds and see that they're moving. When you use radar to look at Venus, you can penetrate through the clouds in the atmosphere, and you see that it has a rough surface indicated like that. Earth, of course, you're familiar with. It's partly cloudy. Those clouds are composed of condensed water. We'll talk a lot about that. Mars has an atmosphere. You occasionally, I believe, see a cloud. A rare cloud will appear in the Martian atmosphere. There's an ice cap up there, but for the most part, you don't see anything moving around on Mars, but we know there's an atmosphere there. We have we've been there, we've had landers there, I mean, not humans, but we've had landers there, and from a number of other clues, we know that there's a thin CO2 atmosphere on Mars. Now, you've all had, I expect you've all had a chemistry course and seen the periodic table of the elements. I just wanted to show this to you to remind you a little bit about that. What are the molecules we're going to mostly be concerned with in this course? What are the elements that make up those molecules? So in red, I have circled the elements that you find most often in atmospheres. So for example, nitrogen in the diatomic form is the dominant molecule in the Earth's atmosphere. Next after that is oxygen in the diatomic form, and there's a little bit of argon also in our atmosphere. There's a variable amount of CO2, combined carbon and oxygen, you can get CO2. I'll show you a list of some of these other important molecules in just a minute, but it's the red ones with their light masses and their preference for either bonding not at all with other molecules or their preference for bonding with other light molecules that makes them good candidates for being an atmospheric gas. In the black circles are the dominant elements in the solid Earth. Sodium, manganese, potassium, calcium, iron, aluminum, silicon. Of course, all these others are found as well, but the dominant ones are the ones I found in black. Now, they, first of all, they tend to be heavier by themselves, and then the way they bond will make them heavier still. And therefore, you wouldn't expect to find them as atmospheric gases. You'd rather find them in some more condensed body like the solid Earth.
Are those found in the outer planets as well?
Question is whether these molecules are found in the outer planets. They all are, yes, in various proportions, though. The ratio of the abundances of the elements does change a little bit from planet to planet, but not dramatically. Planets were all formed more or less from the same type of material, and so if you include everything all the way from the surface, top of the atmosphere to the center of the planet, there's a remarkable similarity between the compositions of the different planets. For example, in the case of Jupiter, it probably has all of these elements. They're probably down in the interior parts of the planet, and up near in the upper parts, you only have hydrogen and helium up in the atmospheres, but those are probably all in there as well. Yeah. Any other questions here? Good. I think that may be, yeah, so here's some of the important atmospheric molecules. You should be aware of these at least. If I gave you the name, you could give me the formula and so on for these. We've already talked about diatomic nitrogen, oxygen, CO2. Methane is an important greenhouse gas, CH4, carbon with 4 hydrogens. Ozone is simply adding another oxygen atom to diatomic. It's just triatomic oxygen. Water is H2O, you know that, diatomic. So we've been through most of these. I won't spend any more. Some of these are important air pollutants in the Earth's atmosphere. So we'll be coming back to studying this group, for example, later on in the course when we talk about air pollution. I'm going to end with that. Let's see. We're going to be, in a day or so, we're going to be talking about the vertical temperature structure on Earth. And since I'm not a very good artist, I thought I would show you this, but this is in your textbook as well. This is the temperature in the Earth's atmosphere as a function of altitude. And it starts around 15 degrees Celsius. That's the example I used today. And then it cools off, warms up again with altitude, cools off again, warms up with altitude. Think about that profile, and in a day or two, I'm going to be asking you to speculate about why it is that the Earth's atmosphere has this peculiar structure. The other planets, by the way, have a structure that's a bit simpler. It cools and then warms. Just one cooling trend and one warming trend in the atmospheres of most of the other planets. So there's something unique about our planet that gives it this kind of layer cake structure of temperature. So let's see, that takes care of that. And let me ask again if there are any questions at this point. Question in front, yes?
Are these slides on like the classes V2 site?
They will be. By the end of the day, they'll be up here, yeah. Okay, I don't have time to start the next subject, so let's call it quits today. When you see me on Monday, I'm going to dive into this review of the SI system of units. We're going to talk about the perfect gas law. We're going to talk about warm air and cold air, rising and sinking. We're going to start into some of the physics of how our atmosphere works on Monday. See you then.